Hello, everybody. Welcome to the third day of Lean Together 2024. Um, the talks are being recorded just so that everybody knows. I believe Zoom is telling you that. And as a reminder, please keep your text discussion during the talks on Zulip rather than in the Zoom chat session so as to not distract the speakers. Um, we are aiming for 25 minutes of talk and 5 minutes of question in each half-hour slot, and I'll be calling on people with questions after the presentation. With that, I'd like to hand the virtual microphone over to Andrew Yang from National Taiwan University, who'll be telling us about Fermat's last theorem for regular primes, case 2.
Thank you to the organizer for such a wonderful event. Today, I'd like to give you a talk about the recently finished project on Fermat's last theorem for regular primes. The talk today will focus on case 2, the second part of the project, the part which I personally participated in. So let's start by defining what a regular prime is. A regular prime is a prime. It is regular if it does not divide the class root of the cyclotomic integers. Now, then the Kummer in 1847 proved the following result, that the Fermat last theorem holds for any odd regular prime P. And by considering the divisibility by P, we can split this into two cases. The first, let me adjust this. The first case is when P does not divide any of X, Y, and Z. And the second case is when P divides exactly one of X, Y, Z. The second case is the more mathematically involved case, and it involves a key lemma called the Kummer's lemma, which we'll be talking about later. And people who are interested in case 1 can look at the ITP paper that was written by the other collaborators. Now, this is a brief timeline of this project. The project started in 2021 in October, and it took about a year to develop the cyclotomic library and to prove case 1. But the project stopped for the Great Method port, and the project was finally ported last year in July. And I joined in September last year, and together with other collaborators, we reduced gradually the big statement into easier and easier statements. And so we'll get to the parts later, but as you can see, the first part is very easy. It only took 4 days to do, and the second part took the most time, but it was mostly tedious just translating statements, well-known statements from textbooks into Lean. And the last part is the hardest since the literature is the most, there's not that much literature on this. And we did a meetup at King's College London in the end of November to crack the proof open. And finally, we finished the project on December 5th, which is coincidentally on the same day that PFR also finished. And instead of speed, we focused primarily on improving the API in MATLib and producing MATLib-ready code. As an example, it was only 1 month since the project ended, but we were able to merge 40 plus PRs and thousands of lines into MATLib, and a lot more from case 1. Of course, this is not possible without the help of reviewers, but this should show that we have succeeded our job in producing MATLib-ready code. Now let's dive into the proof. Now let's let P be an odd regular prime and zeta be a primitive p root of unity. The actual statement we prove is actually a bit stronger, that we prove there are no solutions in the cyclotomic integers rather than only the integers. And we assume that zeta minus 1 divides z. Since zeta minus 1 divides z, we can assume we can do induction on the multiplicity of zeta minus 1 on z. And we have this lemma, which is the main induction step. So you can see that if there are m plus 1 copies of z, we can do some calculations to reduce it into m copies of zeta minus 1. And this is an elementary calculation following the proof in Barvik and Shafarvik. This proof, as I said before, only took me 4 days. And this should be a showcase of the API developed in case one was really efficient and really easy to use. But notice that there is an epsilon one here that is not present in the premise. So we need to do something to get rid of this in order to make this induction step work. And the key lemma is what I talked about earlier, is Kummer's lemma. The Kummer's lemma say that if epsilon is congruent to modulo p to a rational integer, then it is itself a p power. And if it is a p power, we can merge it into the y prime and so get rid of that. And the induction will work fine and the result is done. So the key result is then, how should we prove Kummer's lemma? There are several proofs available, and the proof in Borvik and Shvarik uses an analytic approach, and it uses the connection to Bernoulli numbers and also some p-adic logarithm. But here we follow Thurs-Lang's cyclotomic field, which gives an algebraic approach. It goes as follows. Now, by taking p-1 powers, we can assume that the rational integer is actually 1. And then we consider this field extension. This field extension is a Kummer extension, so it is cyclic and it's Galois. And furthermore, we may show that this extension is generated by this term, these etas. These etas are integral, and furthermore, there are Galois conjugates. And their differences are actually units, so they are distinct modulo any prime. And this may allow us to conclude that this extension is actually unramified. It is a ramified cyclic extension of degree p. Now, by class field theory, we can conclude that p then divides class number of k, and then p is not regular. But of course, we do not have class field theory in our hands. And to properly develop this, we will need like months, if not years, to formalize. So we did a lot more reading in literature. And finally, we found that Hilbert he did cover Kummer's original argument in his number report, and the result we need was Hilbert 94. Hilbert 94 states that if there is a ramified cyclic extension of odd prime degree, then there is a non-principal ideal of K that becomes principal in L. Then such an ideal will be the pth power of such an ideal will be the ideal generated by the norm. So it will be principal in K also. So the ideal will be order P in the class group of L. So P divides its class number. Now, to prove this, Hilbert uses his Hilbert 92, which says that this thing. And this is actually stating that the units group of L is non-trivial. The first comodulo group of the units is non-trivial, but we did not make this connection, and the proof is totally non-cohomological. And assuming 92, we then look at this unit, and by Hilbert 90, we may find a non-unit such that it is the coboundary of it. And then this ideal is then non-principal, or else we can find, or else the beta will be associated to someone in the base field, and then it will be a coboundary of some units, and this is not the case. However, it is principal in L because the extension is unramified, and this ideal is stable under Galois action. So to prove Hilbert 92, we initially wanted to follow the proof in Hilbert's number report, but that proof is not really formalized friendly. But after a bit of thinking, we find a way to abstract some stuff, in particular into modules over cyclotomic integers. This is actually kind of surprising since this statement does not involve cyclotomic integers at all, but we was able to reuse our results on cyclotomic integers to do this proof. And the statement is as follows. Consider a module that is free of rank r times p minus 1, where r is an arbitrary number. Then we may prove that first, M has an linear independent set of R vectors, this R. And second, if such an independent set is maximal in terms of the index, then it satisfies this condition. For a brief proof, we may, if this equation holds, then we may swap out some vi with M and get a bigger independent set. And we apply this theorem onto the relative group of relative units. This idea actually came from Synergy and Dyer's A Brief Guide to the Algebraic Number Theorem. This theorem is not explicitly stated, but is hidden in one of the exercises. Now, we may calculate the rank of this group to be 1 plus the rank of OK times P minus 1. So we may apply this theorem to get this result. And this result is the Hilbert 91. This gives us a lot of units that is not the coboundary of another unit. And so we now have to massage in some unit that has norm 1. First of all, notice that there is a non-trivial relation like this because the R is greater than the rank of OK. Then we may factor out the P from the AIs to get something like this. Now, and some AI will be non-divisible by P. Now, if the base field has no primitive teeth root of unity, then we're done, since the part inside the parentheses is already 1. And so the product of that is these have norm 1, and this is not of the form of a coboundary. And if K has a primitive root of unity, we can still apply a similar approach, though more convoluted, to get the similar result that I will not go into deep here. So to recap, we need ZP cyclotomic modules to get Hilbert 91, and together with ramification of infinite places, and also the Dirichlet theorem on units to get Hilbert 92. And together with some results on unramified extensions, we get Hilbert 94. And to apply Hilbert 94 on the field we get on Kummer's lemma, we need some results on Kummer extensions. And also we need some more results on ramification, in particular different ideals. So now let's take a look into all the formal definitions we got in these order. First of all, it's the ramification at infinite primes. We define such a class stating that an extension of field is unramified at infinite places. We show that if the dimension is odd, then this is indeed unramified. And also we did a calculation of the cardinality of infinite places in this context. Then for unramified at finite primes, we had a similar class. And the main result we need to use is that if an ideal is stable under the Galois action, then the conorm of the extension is still the ideal itself. This is used to prove that the thing is actually principal. And next, we need some results on different ideals. We define different ideal between an extension of domains, and it is defined as the inverse of the trace dual of the integers. And the main result we need is that if the minimal polynomial of x and its derivative falls in the different ideal, in the case where x is a generator, a simple generator of the big field. Of course, this result follows from the Kummer-Dedekind theorem if B is generated by X, but this is not necessarily the case, so we need to reprove it here. And some more ramification results we get is this one. If E is the ramification index of P, then P to the E minus 1 divides the different ideal. And in particular, this helps us conclude that if P does not divide the different ideal, then it is unramified. Of course, the inverse direction also holds, but we did not need this in our project, so we did not prove this. Finally, all these gives us this statement, which says that if the minimal polynomial of the generator is separable modulo a prime, then the prime is unramified. This helps us conclude that every prime is unramified in the field in the Kummer's lemma. Of course, we also had results on Kummer's extension. Mainly, we showed that an cyclic Galois extension is precisely those generated by a root of some element. And all this makes us conclude these two theorems, Theorem 92 and 94 from number reports. And we conclude that Kummer's lemma holds, which is if a unit is congruent modulo p to an integer, then the u is a p power. So all this gives the first main statement, which is in terms of the cyclotomic integers, and also the main statement, which is in terms of integers, and it's case 2. And together with the case 1 effort, we have showed this result, where is regular prime, as we just said, is if it's coprime to the cardinality of the class group of the cyclotomic field. And Fermat's last theorem holds for regular primes. Now, I will conclude with some remarks that we found during this project. First of all, it's easier to work with an AKLB setup, which is we have 4 types AKLB, and we assume that A is a Dedekind domain, K is the fraction ring of A, and L is a finite extension of K, and B is the integral closure of A and L. This has the benefit of being applicable to both a finite extension of abstract Dedekind domains, where we have A and B, and the K and L are fraction rings, and also applicable to an finite extension of number fields, where K and L are given, and A and B are the ring of integers. This is just like the is localization predicate or the is cyclotomic extensor predicate. And furthermore, it helps us avoid this big problem. This simple code snippet is just defining M to be a submodule of OK and OK, but this takes 13 seconds to compile. This problem is already reported on Zulip, and I think there are smart people already working on it. In particular, making the structures flat in MATLib seems to reduce this to 4 seconds, but it's still long though. And in some files where we had to work with ring of integers and we had to encounter this problem, we had these kind of things where we handpicked the instance that we want, but this is not really scalable. And of course, these approaches do have their cons as well. The biggest one is that it takes 7 lines to define, and a lot of proofs start with these because these cannot be inferenced by our usual type plus inference. But of course, these should be able to be solved easily with a tactic or something similar. So I believe this is not a long-term problem. And finally, I'll end with some potential future projects. First of all, it would be nice to have analytic class number formula. And together with the work by Narayanan on p-adic L functions, we may able to connect regular primes to Bernoulli numbers. In our project, we do not have any instances of regular primes. We only prove that 2 is regular. So without a real criterion for regular primes, our project is not really applicable to any real numbers. And on the more algebraic side, I think after these cyclotomic library, I think Kronecker-Weber will be a good target to approach next. And if we have some more group cohomology, and in particular some Herbrand quotient, we might even be able to tackle some calculations in global class field theory. And in particular, I think first inequality would be something easier. And finally, we might just be able to remove the superfluous hypothesis that P is regular. That's the end of my presentation. Thanks to all the contributors to the project, Alex, Chris, Ricardo, Eric, and Ruben. And special thanks to Patrick for the amazing blueprint framework, and also Utensil for helping us transition our blueprint into Lean 4. And our work builds upon a large chunk of MATLAB and a lot of big theorems, and especially Hilbert 90 by Amelia and Dirichlet's unit theorem by Xavier, and also a big chunk of ramification results by Anne. And of course, all the other community members and all the MATLAB contributors for all the other amazing bits in MATLAB. That's the end of my presentation.
Thank you very much. If you have a question, please virtually raise your hand in Zoom, and I'll call on them as best I can in the order in which they are raised. Kevin, you've had your hand up since before question time began.
Yeah, apologies.
No, it's fine.
So we have, I think, Fermat's last theorem for P is 3 already. So the first non-trivial case would then be P is 5. So how much work is needed to prove that 5 is a regular prime?
I think Xavier is improving on the Minkowski bound, and we should get immediately from that 5 is regular.
What is your definition of regular in the formalized definition?
The formalized definition is
you just went with
coprime with class number, yes.
Yeah, so, Kevin, I'm doing P equal 5 just for fun, and it should be very easy. The only thing we are missing is that the number of complex places is 4. But I mean, this is nothing very difficult.
2, right? 2.
2, yes, sorry, yeah. Yeah.
Okay. So, and it's a PID, is it? Z to 5 is a PID.
Yeah, this is thanks to Xavier's work.
I see.
That it is a PR, fabulous. But it will be soon in MATLAB.
I have 2 other questions, but I'm happy to let other people have a turn.
Any other hands to be raised? All right, Kevin, number 2.
So you were talking about Kronecker-Weber, and my memory, I learned this when I was your age by going through, there's a proof in the exercises in Marcus's book on number fields that's completely elementary, as I recall.
Yeah.
Is that the proof you're thinking of, or are you thinking of another proof?
I'm thinking of that proof, yes.
Oh, you are? Yeah, I can't remember what goes into it, because it was a long time since I was your age. Okay, so
I remember it's just mostly elementary calculations, and I think it's viable.
Okay,
the proof I know goes via the local field case first. Is that what you're thinking of?
I don't think there's any local fields in
I don't think so.
markers.
I don't recall the details, but
yeah, the proof in Washington goes via the local case first. But I think the proof in markers, I just can't remember at all now, was the kind of thing I could understand when I knew nothing. But my final question was, I was quite surprised to see your definition of different. Are there no hypotheses? In my mind, difference and discriminants, you need some kind of hypotheses to make things work. But that was before I was somehow leanified. There's
the
no
different
data.
ideal itself does not need much hypothesis. It's just the trace dual and restricted onto A. But to really show that this thing actually falls in A, you need Dedekind domain.
You don't even need flatness or something. It never occurred to me that you could make the definition in such generality.
I can make the definition, but it doesn't really work well unless you assume it's Dedekind.
Yeah, because I remember having a long discussion with Conrad once about the correct generalization to. If you look on Wikipedia for the definition of different, it just sticks to like number fields, which is sort of clearly not right. But somehow I thought that we had some sort of ideas about the extension had to be local complete intersection or something, all kinds of crazy ideas. And you're just telling us we're completely wrong and it should just be made into huge.
No. It only works well when Dedekind, but the definition itself doesn't need it to be a Dedekind domain, so it doesn't appear there.
Yeah. Yeah, very nice. That's something I just learned. Thank you.